First, let me say that what I'm talking about is a joint work with Arye Juhasz. So then, while I'm discussing several results, let me first issue a disclaimer, because it is a very complicated work with and involved arguments. Before the full text exists, one cannot actually claim the results. So actually, I'm trying to describe the ideas behind these activities. So now I will proceed further. The starting point is, of course, the usual small cancellation theory. In the usual, as it was, for example, geometrized by Lindon, we start with a Van Kampen diagram. So if every region has a label which is a relation in the group, then on the perimeter we read a word that is in the normal subgroup generated by these relators. Now, it turns out that if every common part of the regions is small, then every inner region will have many neighbors. And this, let us call such maps hyperbolic. It will determine the structure of this map and also of what we can read on the circumference of it. So here, actually, what we need just data about the combinatorics of the relators, because they have to they cannot interact between them for a long part of it. Now, but this actually we would like to deal with a more general situation when we have much more relators in the way that they could be put into what I call layers. You can imagine that this is the shortest relator, say from one, then the second group, the third group, etc. And then actually what happens is that only the interaction, so when you take a word of a belonging to some R and some S for R less than S, then the interaction could be actually on even a half on the part, or more than half on the part of the smaller relation, and maybe very small on the part of the big relation. And this is unavoidable. So you cannot put this to this kind of structure. So then there are different ways to proceed with this situation. One of them was when we consider so-called graded Van Kampen diagrams. So here each relator is graded according to which layer it belongs. So we have the first layer, the rank 1, rank 2, etc. And now in a kind of there was different variants of the generalized small cancellation theory. In one I developed in the early 80s, there was the idea to take a kind of absorption process, in the sense that the regions of all ranks from 2, 3, etc. will absorb all the, divide between themselves all the regions of rank 1 according to certain preference. And then we will have a new diagram, we will call it a derived diagram, but we have here a new region where we have this main region and all the regions of rank 1 that it absorbed. So now we have a new derived diagram. Then we repeat this process. Now the smallest rank is 2, and then all the regions of rank 3, 4, etc. absorb, according to a certain preferences, all these regions of rank 2. So now we have only even bigger regions of rank 3, etc., etc. So we continue this because it's a series of derived Van Kampen diagrams until we come to the last situation that only the highest rank exists. So inside is the original region of the highest rank, then and many absorbed regions absorbed by this process. So each of these regions is just this is a big empire and this is metropolitan. Now, but then we would like to have some information about this, how it behaves. But here we have an obstacle. The obstacle is that we may not have a direct contact between these regions, between the regions, between the original regions of the highest ranks. There are a lot of regions of smaller ranks. So how can we actually extract any interesting geometric information from this situation? Actually, there was some remedy for it. This is called the contiguity diagrams. The contiguity diagrams means that when we have these regions of the highest rank, so we actually can find a situation, there is a kind of a bridge between them, and here this inside is filled by diagrams of smaller rank. So again, we do not have a direct contact between these, but some kind of the structure. And now, in a sense, the problem remains, because we know that there is certain combinatorial structure of the boundary of this original region, also some combinatorial structure on the boundary of the second original region, but between them there is some diagram. All of them have regions with smaller ranks. And now how can you extract from this the claim that this is small in a certain measure on the relation? But this we need if we would like to make a claim that it need to have any inner map in this derived diagram have many regions. So actually the way to deal with it was the following. We have a certain, what are our resources in order to improve the situation? Now, we have a group with generators and relations. Now, but we can try to have some canonical form, both of words and of relations. So then we will have the same group with another presentation, but here we have, in a sense, an improved form of these relations. They should be chosen in a certain canonical way. Now, how does it help us? Because if we assume that both this is a canonical word and this is a canonical word, then actually we can ask how behaves the quadrangle of canonical words. Now, and here it could be a kind of a naive expectation that it could be just degenerated to a quadruped. Unfortunately, this is not true. So we cannot just by a clever choice of the relations to collapse the contiguity diagram, because it turns out that only by the canonical form, if we will take now the canonical triangle, the triangle of canonical words, it would have such a form when, except in the simplest cases, by a theorem of Gromov, we cannot bound these lengths. So as a matter of principle, we cannot do better in the way that only if all of them should be bounded, then the group would belong to a very simple class, a free product of cyclic groups, and this is not the case. So then one have to squeeze out something in between. The point is that it turns out that we can take, by the way, what I'm telling now, this is the approach, so that in a case of a small cancellation group, we could choose the canonical form in such a way that the canonical triangle now has the following structure. Here is some word. Now, a relation. Now we have a certain part. Now in the middle we have a relation. Again we have a certain part. And here we have another relation. So here is like it looks. So, but here instead of a triangle, we have this triangle that we had in general, we are able to squeeze it to this form. Now, but still one cannot have a bound on the length of this part. All of these parts could not be bounded by lengths. But it turns out that no, it is just 4 regions. I mean for a small cancellation group, in an ordinary sense, there would be just 4 regions. Yes, but we cannot bound these lengths. This, which I marked by red, the lengths cannot be bound, but one could obtain a control over their structure. Okay, actually, let me say this way. This was in the second part of the generalized small cancellation. Now, and the first part was actually appeared. Now, and then appeared the remarkable works by Olshansky that actually did this in a quite different way, but also coped with these problems. So I just put it aside. No, he did it another way. He did this in another way. This approach I used to take a canonical form, but for me it was it was half written, but never published.
So this statement is not written anywhere.
Yes, yes. So this is an old story. Now, if one takes this, instead of taking this, the usual small cancellation, but this is generalized, then one have an analogous picture, but now this becomes a kind of a fractal triangle, by which I mean that each of these triangles itself has a similar structure here. Here a small relation, etc. for all of them. And then the same in all the ranks, and also the same kind of control for each of them, etc. So still there is a kind of structure, yes, for these canonical representatives. Now, the point is that when we know that this word has a certain combinatorial structure, be it a power of a, be it a, just in the Burnside problem, it will be just the power of a word, or it could be some product of powers of two words, etc. Now one can orchestrate the choice of this canonical form, that it could not take neither many powers of a single word, nor if we have two words, it would not be power one, power, etc., in the kind of the structure we have in the n-Engel group, for example, or actually in any kind of structure. So we can arrange the choice of the canonical word such that it could not be compatible with the combinatorial structure of our relations. And then, of the result of it, when we turn to the contiguity diagram, after appropriate choice of this, it will, in a sense, it will collapse. Here, something else. This is short in certain terms, and then here we have a direct contact between these words. So then we can also use in the combinatorics of groups of this word to decide whether that is short. Now, this is in the case where we are dealing with groups that are inductive limits of hyperbolic groups. Now, as it is dealt in the case of the general small cancellation, including the work of Elshansky and all subsequent works. But now the question is whether it is possible to extend this idea to a case when the groups have many commutative relations. For example, the n-Engel groups have commutativity inside it. For example, to take the n minus first commutator, and then it will commute with the last letter, etc. So these groups all have a lot of commutativity. So actually, commutativity corresponds to the zero curvature. So the groups which we have is figuratively saying inductive limits of group of non-positive curvature rather than negative curvature. So the question is whether one can take the same approach in this case. Now, what turns out is something else. We just cannot hope to have such kind of a triangle. For example, we would like what happens for the plane. So for the plane, we simply do not have a canonical form that with these properties. One thing one can do is we will take the canonical form depending on the direction. We will one for the one direction and another for another direction. So we do not require that the canonical form of the inverse should be inverse of the canonical form, because this is impossible in the plane. So, for example, if we have in the simplest case of the plane, we can look 2 points, and then we take this simply canonical form. Now, if we look in the opposite direction, then the canonical form will go this way. And then if we have 3 points in the plane, So it goes this way, this goes this way, and this will, excuse me, no, sorry, horizontal first. And then, and in the opposite direction, this way, and this way. So even the canonical triangles obtain some unusual form. And actually, we need, in the general, we have the behavior of both types together with some additional idiosyncrasies. So we cannot hope so that the canonical form will behave in the usual way. Now, but nevertheless, what will be achieved? Then it turns out that the canonical form will give us, in one case, such a thing, in another, this. So what will be in between? This will be just equal one to the other. And then what we need to show is that it happens the following thing. That this part, where this word is precisely equal to this word, could be prolonged unto an annulus, so that exactly this word inside on the two sides of annulus are equal. So we have here a kind of a situation when we have this annulus around this. Then we can make a surgery inside this map, just to add this here. And then just these two will be collapsed. So, after all, we return to a direct meeting between these two regions, because these two are just cancelled out. So this part, now it is the same relation here, will be equal to this part. So we need actually a combination of two things. One, taking the canonical form. Now, the main claim is that after all, the canonical form will give us such kind of a...
The structure consistency travels to look at symmetric space. They are taking it as it were. So there is more absorbing the action of the Euclidean group there. And the question, why is the way performed consistent when you go from one to another?
Exactly, exactly. The natural suspicion is that it would go... One has to explain why this kind of situation could be prevented.
Yeah, why it doesn't turn? You go around, why it doesn't turn? It's like Kampen in symmetric space. They are really useful.
Yes, so exactly. Now,
these are wide groups. So say you have this kind of wide group of streams.
Yes. So now when we are going to the details of, so actually this was on the general plan. Now one has to explain how one tries to find a symmetric form that will have all these kind of conditions and something else. Because here the symmetric form, the canonical form will depend on the direction. And this brings a lot of additional complications. But what?
But another question, this n-Engel group, they don't cancellate the important part, not cancellate the important subgroup, instead of n-groups. Or they're equal or they're also important.
Now, in these cases I'm considering there are only a billion. The question whether or not one could deal with nilpotent, it is very interesting question, but it leads to additional complications which are now absolutely unable to say whether it could be overcome. So this theory is just a bit, because in nilpotent you have actually positive curvature as well, so I don't know. In any case, what happens here is the following. So let me recall first how was defined this canonical form in the case of the hyperbolic groups. So actually one was able to define all this by induction of rank. So I'm just referring to the highest rank in question. So one is able to define a one-layer diagram. When I'm saying one-layer diagram, I mean that the highest derived map behaves like a one-layer diagram. So inside each of these, one has the original relation of the highest rank. Now, here we can assume that both sides of it are canonical in the previous rank. So we have kind of contiguity diagrams with the sides of it. Then we use the same technique in order to move the region to the boundary. So we can assume that at least on one side of the boundary it is just direct contact with this region, but not of both of them simultaneously. We can choose this side or that side, but not both of them. But in any case, it means that inside this word, we have a biggest subsegment that it is actually a part of this relation. And this for all of them, and for symmetric reason, we have it on the other side. When we move this to the other side, we have the same. So in this case, we have such words. And then we, in order to make our choice, we have to decide what side of this one-layer diagram we will choose. We can choose, in certain cases, the upper side or the lower side, etc. So then reduces us to the element in the previous group when we take, instead of being in the group Gn, which is x R1 to Rn, we are now in the group Gn minus 1 R, or maybe prime, to Rn minus 1 prime. So then, this is a lifting of this element, which is achieved when we just choose sizes in the one-layer diagram. Now, how we choose sides? We consider all possibilities for this, whether to go this way or that way, or maybe this way, and then all of these will be segments of the original relation.
How much incompatibility you are? Does every element produce a continuing element, or the subgroup kind of discretely a relative velocity? So there are completely opposite cases to this picture. And these are practice, right? There are very many opposite cases. How dominant it is? Are these dominant like symmetric space in every element almost everyone is commuting? Right? Or on the contrary, they're very rare in this space between hyperbolic, which we usually call.
Oh, yeah, we tell you in a moment. So, if it is hyperbolic, so then...
Hyperbolic in the flat direction, maybe transversal hyperbolic, or it may be not. I mean, there are very many different cases. They are very different. So each case you consider, like symmetric space. Look at the Briouatti's building of rank 2. So, it's okay for you? Would it be kind of example you can consider?
No, I cannot tell you because I'm looking on the structure of the relations. Just
if this group will be of your class. Like lattices and Briouatti.
No, lattices. No, I don't think so.
So what you can do? What abstract you can do?
Okay, so yes. So the conditions which I will say here assume, for example, that we have a word of some too complicated word, some of two elements. For example, the n-Engel word or some higher commutator. So, and then take Rn be the set of groups F, A, N, Bn, where the sum in measure An plus Bn will be between in sum this power. So we take, this is the way we take the lengths of An and Bn, and then we divide it into layers according to the sum of the lengths of these words. So all of them could be the same word. Actually, one can look of the more complicated word, situation, but it doesn't matter. So for the simplicity, this situation, we take a group where all the relations are the same complicated word of two words. In this case, A will be okay. Now, in the case when we had negative, negative curvature, then there was one which was the shortest one. So we can just unambiguously choose one of them by say for the lexicographical order. And this will be our choice. Now here, because of the commutativity, we may, and we actually do encounter a situation that both words may be equal. And this is the new point. This way to choose it breaks down here, because this is exactly the same word as here, and this is a commutator. Now, and here, by the way, when we constructed this one-layer map, it also was involved with construction because we needed to apply arguments that will give us such kind of a picture. Now, but here, we just may have such a situation where it is part of this, they are symmetric, and therefore we cannot resolve the ambiguity in this way. Now, it turns out that in this situation, when these are equal, we can consider the same repeating. So we have here a kind of a strip. Now, and this strip actually, as to say, is a quantum of a flat in this map. So we have, it goes in both ways indefinitely. If the next now may have the same structure, now when we have two strips, so what could happen? Only they could be connected one to the other, or it could be a situation then one strip, one vertical strip goes this way, and the other at some point has a minimal distance of this, and all other are of bigger distance. So then here we leave this part of the flat, and now we go to another situation. So in all the situations, so only when we have a strip after strip that are connected through the whole vertical axis, then we are in the same flat. When we encounter the situation, we leave one flat, maybe we have another flat number of times, maybe yes or not, we continue to go here. Now, all this, we return now to the situation with the words. So actually, I can consider this as a word with two variables. So it could be that we have a kind of a situation that it will be a pass in this graph. Because, for example, if this is AN, and the other will be Bn, so it will go around. Now, what happens here is that we first take the canonical form for this word and for this word, and we have to know how to glue this. So this also, in fact, we need the canonical form not only of words and of cyclic words, also we need to define the canonical form of such pretzels, as to say. It could be also in this way, or it could be in this way. All these cases we need to define what we mean by the canonical form. And then, when we go here, every Arye relation is actually as to say, biperiodic word in these periods. We maybe go this way sometimes, then this, etc. So all our relations are biperiodic words. Now, the question is whether we go inside some flat for all of these flats in a certain rank, or we encounter a place where it leaves the flat in the way that way I pointed here. Excuse me? Biperiodic, I mean just a power of A, a power of B, a power of A over B, in this sense only. Yes, of course. So I mean, here we have a closed path in this graph. It may be some power of an, then some power of b, maybe some negative power of n, etc. Just all of these kind of words. I call them just for shortness biperiodic, not as elliptic function, but in this particular sense. Now, then, if there is a situation, then we have our ambiguity resolved. So one is shorter than all of these competitors. So then it means that every time we blow this point, so then, let me explain it this way. When we look on the canonical passes, we ask how it depends on the ends. So if we have here a canonical path, we take a perturbation of the end and then look how it goes. If it inside one flat, then it will go this way. Or it could be that it shortly it goes to a flat and then but if inside it there is some collapse of this form, then after a short void it will go to the same. So the perturbation of the end will not last more than few B periods, and then these passes will go identically in rank n. It means it will be in the smaller rank when we return to the big picture. So we have actually just a dichotomy. Either the whole of it is inside this flat, and then we will obtain exactly this picture that I had here after period that it goes to this, or it collapses to the same, and then it reduces to the previous rank. So we have this dichotomy. Then we have to worry that some of the cuts, because it would be for every n, it should not diverge, it should converge. So actually it is one of the most subtle parts of the argument when we do the induction of rank and we cut the ends so until we enter the flat. So this is a flat. It may be even absent when we obtain this collapse of this way, when we do two strips, or when just the choice is lack of ambiguity. Now, but then we do the same thing in the rank n-1. I'm proving. the statement is that when we have this diagram and the no, this is exactly. I'm saying what should be correct, and then the conditions just we follow what should be satisfied in order this statement hold true. So what statement we need here? We need here the statement that when we take this is actually a canonical form. Now we take here a perturbation of one end and we look how it goes. Now then the claim is that after a short time means in the number of B periods of this word, it comes in the situation of a flat, and the end should be also for different. So it means that the claim is that after a cut of the ends, the contiguity diagram reduces to a flat. Now, because this flat is a part of the B periodic word, here on the boundary of a B periodic word, so we have many B periods. So this actually means that we have a work inside this, and then the flat just goes above this, so but exactly the same way. Then when we make the full relation, so we return exactly to the same place, and do not have this kind of spiraling, because everything happens in the flat in which this pretzel exists. So this is the way how we prevent this problem. Then one have another thing, that when we reduce the rank, then this number of cuts should converge. Yes, and then finally,
this creation itself has no rank, right? You artificially divide the blocks when you prescribe the rank, right?
Excuse me?
Like in the side problem, rank is artifact.
No.
It's inherent to the self-relation, has no grading. You impose a grading.
Of course, no. But once imposed, it stands by itself. Yes. So actually,
we have condition to know this will work. We have the grade part condition here spread. Yes. There is no means for any condition.
Actually, one has to. The smaller the C, the healthier for the argument. So we have to make these slices thin.
But the thin, they are harder to prove something because they are mixed up.
Now, then we just make longer the words. And in order to remedy this difficulty, we just make long this. For example, in the case of the n-Engel group, just I would say that 40 is more than enough.
How much was it?
40. Okay. Excuse me?
For n-Engel groups, can you show that they are not nilpotent?
No, if this mechanism works, then you have a kind of a solution of the word problem, which will show that you have definite word, even the group with 3 generators will not be nilpotent. You can just write words in 3 generators that will not have big parts of it, because this ultimately means a kind of a Greenlinger lemma should hold if this construction works, and then you also easily construct words that do not have big parts of the relation, that therefore are different from one. So the whole thing is to show that this construction works.
You have to prove the relation don't cancel each other, right? This is the point. The relation do not cancel each other. There is, so to speak, no obvious relation between relations.
Oh yes, but now the point is if this is achieved, then we come to the direct contact. And this is a matter of combinatorial of the words. And this is a problem that it is much easier than everything else here. Let me also say that this problem about n-Engel groups was posed by Professor Plotkin in the early 50s. Virginia? Okay. In any case, I believe that the same technique works for a wide range of situations when actually one looks, for example, a word in a commutator x, y, etc., then the same, of course, long enough, and then the same kind of technique is applicable, so it reduces, after all, to the interaction between the combinatorial.
Combinate exactly what you think you can prove. Exactly, just statement with a statement. If there is, just write it down.
Okay. Okay, and now, yes, as for the same constant will do. Okay. Then, if we have this kind of relators with all x and y substituted for
all pairs of elements in the groups is space. All pairs.
Yes, of all pairs, exactly.
Including identity, one may be identity.
Including?
If somebody is identity or something.
The commutator.
So do you want three cases? I'm afraid there is something. For all elements, really for all.
Oh, free, of course. Okay, because you wish that it will be a specific statement of.
So it's specific, you might be commutator deprivation.
This is a normed commutator.
This example here.
Yes. Actually, in this case, again, you can follow the combinatorial of the words here, and you have exactly the same effects in a little simpler. That actually the n-Engel case is more difficult.
So how long this must be?
40. 40 years.
And for n-Engel words? Like
No, I mean, for n-Engel, we have just x, y, y. And here we have just mixing the x and y's.
Number of lengths.
At least 40. 40.
40, it's not 40,000.
40. No, because you see, this is a commutator, so it doubles and triples its length with this. So it will be it's a very long word.
Because for one side you cannot make the question, right?
No, this situation, this actually means 2 to the power 40.
It's 2 to the power, 2 to the power. Oh, wait, sure. This means theoretic combinator.
Yes. No, of course not, because they have lots of commutativity. Oh no. If they are relatively, I don't think so. So
with respect to flats.
No, because the flats may interact also between themselves, etc. It is actually you can describe it, but it is not something relatively parabolic.
Next time.